Thank you very much for the opportunity. Good afternoon, ladies and gentlemen. My name is Putu Dodi Sutrisna. I'm from Chemical Engineering Department, University of Surabaya. Today, I would like to present our research with the title of The Effects of Material to Solvent Ratio on the Performances of Natural Dyes Extraction. I would like to start my presentation with the background of my research and then move into the experimental techniques, and I will close my presentation with results, discussion, and conclusion. The development of creative industry in Indonesia has improved the supply of fashion into the market. The fashion industries need coloring process in the process production. Recently, the fashion industries tend to use synthetic dyes for coloring process due to the ease of supply and cheap. However, the synthetic dyes usually contains heavy metal that can pollute the river, lake, and other bodies of water. Hence, it can endanger our life. So, in recent years, many researchers have tried to utilize the natural dyes to be promoted as dyes for fashion industries. The main challenge for the fashion industries to utilize natural dyes is the standardization of extraction process of natural dyes, as the natural products vary in their physical and chemical properties. So, this study tried to analyze and conduct experimental works on the extraction process of typical plant for dyes production. And in this research, we choose mango leaf or Mangifera indica leaf as the source of yellow color. The source of dyes is currently used by our industrial partner in Central Java, Indonesia, where they produce batik fabric as their products. And then from the theoretical point of view, the yellow color in mango leaf comes from the chemical, namely mangiferin. Mangiferin is included as xanthan group that provide yellow color. The derivation of mangiferin is eosynthetic acid that mainly produce yellow color from mango leaf. So, the experimental techniques used in these experiments vary three variables, including extraction time, the type of solvent, and the material to solvent ratio. As we can see here, we tried to vary the material to solvent ratio between 1 to 7 and 1 to 15 material to solvent ratio. We use water as the main source for solvent to accommodate the real application in the fashion industries. And then for the extraction technique, we compare two different techniques such as Soxhlet and reflux. For the experimental procedures, firstly, we dry the material and then we reduce the size of the material using crushing machine, followed by screening and extraction process. After the extraction process, the products were filtered, evaporated, and analyzed for their absorbances using spectrophotometer UPVs. And then we also calculated the yield and analyzed the sample using LC-SRMS to define the best technique that can maximize the extraction process. And then we move into the results and discussion. As we can see here, the absorbance trends versus time for methanol solvent show an increase for 5 hours extraction process. In the case of solvent, the usage of water did not show any significant absorbance rise compared to methanol. Thus, it is indicated that the Soxhlet method for leaves extraction was more suitable with methanol solvent. Due to methanol volatile characteristic and lower surface tension than water, the extraction process in the material core was easier. Furthermore, the functional group in methanol, such as OH group and methyl group, could dissolve either polar or non-polar compound, which could extract the mangiferin better than water as a universal solvent. For the reflux extraction process, both of the solvent for mangiferin extraction by reflux method generated a high increase of absorbance with extraction time. However, methanol solvent still gave a higher absorbance than water solvent. Therefore, it can be concluded that methanol solvent produced a better performance for both extraction methods. This phenomenon happened because of the flavonoid compound that had the OH functional group in mangiferin, which had similar polarity with the solvent. So the materials to methanol solvent ratio was further discussed. An extraction results of Mangifera indica by reflux method with methanol with different material to solvent ratio are shown in this slide, where we can see that the 1:7 material to solvent ratio gave higher absorbance result than the 1:15 ratio. A greater amount of solvent produced a lower absorbance because a large amount of solvent diluted the sample containing color substances. In terms of yield, as shown in these two tables, the percentage of yield for both extraction methods by water and methanol solvent were not proportional to the increase of extraction duration, where a maximum yield was achieved at 4 hours of extraction. These results were also in line with the spectral analysis. But overall, the 1:7 material to solvent ratio generated a greater yield value than the 1:15 ratio in every method and time of extraction. According to literature, a similar polarity between material and solvent played a big role in the extraction success. This statement was proven by the yield percentage in these two tables, which a higher yield was resulted from using methanol solvent. And then we also tried to analyze the existence of mangiferin in mango leaves by using GCMS and LC-SRMS. The GCMS we used in this research failed to detect the existence of mangiferin. Hence, we tried to use LC-SRMS, and from this analytical equipment, we can see that mangiferin can be detected at following retention time that give M/Z that is suitable with mangiferin and in accordance with the literature. The coloring result of Mangifera indica extraction produced a darker color in the 1:7 materials to solvent ratio than the 1:15 ratio. The pale color on the right-hand side might be due to the coloring agent dilution in the 1:15 material to solvent ratio. So in this case, we can conclude that 1:7 ratio is the best material to solvent ratio in our experiment. Then to conclude my presentation, I would like to say that this research has conducted the extraction process of yellow color from mango leaf. The extraction process requires different process conditions to optimize the yield of dyes produced, and then the methanol was found to be the best solvent for Mangifera indica extraction from spectrophotometer and LC-SRMS analysis. Regarding the material to solvent ratio, the 1:7 ratio showed to be the best extraction performance for both materials. And the application of color into the fabric shows a promising result, and further results are still required to enhance the coloring process of fashion in industrial scale. Last but not the least, I would like to acknowledge UBAYA or University of Surabaya and also the restricted team for the funding provided for this research. Thank you for your attention and good afternoon.
Assalamualaikum warahmatullahi wabarakatuh. Ladies and gentlemen, I'm Reza Karina Rahmadi, an electrical engineering student from Pertamina University, and today I'll present you about my thesis that titled Textile Wastewater Purification using Corona Discharge Method. And here are 4 topics that we will discuss. The first is introduction, the second is experimental method, the third is result and discussion, and the last is conclusion. While we're entering the first topic, introduction. The background I took this title for my research is the environment. Environment is everything that surrounds human and greatly affect human life. So that if there is experimental problem, it will also affect human life. There are 4 kinds of experimental problems, and I take experimental problems in the form of liquid, or commonly called wastewater. What causes it? There are several sources that cause wastewater, and I focus on industrial wastewater because industrial wastewater have larger scale rather than the other sources. For example, textile industrial wastewater. And here are some representative data of textile wastewater from various regions in Indonesia. The highest dye concentration is 3050 from Sidoarjo. Well, to process the wastewater, here are some solutions which is offered. And I took the ozonation system to purify the wastewater. The advantages of this system is it can eliminate color, odor, and taste in water, can decompose organic compounds, experimentally friendly, and also can sterilize microorganisms. While the disadvantage of the system is requires pure oxygen for a more efficient process. Then how to make an ozone for ozonation system? There are 2 methods, but I rather choose corona discharge method because it is experimentally friendly, even though it requires good protection because it uses high voltage generation. In ozonation process, we need oxygen, either pure oxygen or free air. Then at the end, when ozone, then the ozone will react with wastewater so that the molecules of the wastewater can be broken down. The next is experimental method. Here is the flow diagram of the purification. There are electrical parts such as flyback converter, and also the reactor part such as needle field purification reactor. From the table, there are 2 cases that we will experiment in this research. In the first case, we will know that the relationship between the number of circulation and the purification result. And the second case is we will know the effect of oxygen, either pure oxygen or free air, on the purification result. And here is the purification procedure using pure oxygen. The first is making synthetic wastewater of 10 milligram per liter. The second is entering the synthetic wastewater such as 50 milliliters. Then flowing pure oxygen of 0.2 liters per minute. The fourth is processing wastewater according to the table of the circulation. The fifth is measuring the dye concentration, TDS, and the pH of the wastewater after the purification process. And the last is repeating steps 1 until 5 for the other circulation. And next is the purification procedure using free air. In this case, it's the same with the recent procedure, but the free air doesn't have a flow rate. The next topic that we will discuss is the result and discussion. There are 4 topics that we will discuss. The first is dye concentration, the second is TDS, and the third is pH. The last is purification efficiency. Here is the picture of wastewater purification result. We know that the more the more number of circulation, the purer wastewater will be. And here is the graph of dye concentration. From the graph, we know that the dye concentration tends to decrease as the amount of circulation increases. And here is the calculation of removal ratio of dye decolorization. And this is the graph. From the graph, we know that the removal ratio of the dye concentration tends to increase as the amount of circulation increases. We can analyze that the more the circulation, the clearer the wastewater produced from the purification process. The second is the highest removal ratio is in the sixth circulation, which is 92.94%. The third is the highest removal ratio using pure oxygen was 92.94%, while using free air was 61.44%. And the last point is the removal ratio using pure oxygen was greater than using free air. The next topic is analysis of TDS. Here is the graph of TDS on the purification process. From the graph, we know that the TDS level tends to increase as the number of circulation increases. And we can analyze that the TDS level tends to increase as the number of circulation increases due to the oxygen oxidation process in the electrode used, which is copper. And here is the chemical reaction. The second point is the more the number of circulation, the greater the TDS level produced. The next analysis is analysis of pH. Here is the graph of pH of the purification process. And we know that pH level tend to decrease or become acidic as the amount of circulation increases. And we can analyze that the level, the pH level of purification process is decreasing due to the hydrogen ions formed during the purification process. The more hydrogen ion produced, the more acidic the pH value will be. And this is the chemical reaction of the process. The second point is when pH level using pure oxygen and using free air doesn't have much different on the result. It shows that the oxygen content doesn't affect the pH level of the wastewater. Then the next analysis and the last analysis is purification efficiency. Here is the calculation of purification efficiency. Then we know that the graph is like this. From the graph, we know that the purification efficiency tends to decrease as the amount of circulation increases. So we can analyze that the efficiency of the purification system with pure air is higher than the free air. And the second is depend on the first until sixth circulation, the largest average value of the purification efficiency is when using pure oxygen, which is 0.1 milligram per watt hour. The next topic and the last topic is conclusion. From all the discussion before, we can conclude that first, the ozonation method can reduce the dye concentration, and the highest removal ratio of dye concentration is in sixth circulation, which is 92.94% of dye reduction. The second is the greater number of circulation, the clearer the purification wastewater will be. The third is the more number of circulation, the higher the TDS level due to the oxidation process. The fourth is the more the amount of circulation, the more acidic the pH level. Due to the increasing number of hydrogen, the purification process. The fifth is based on the calculation of the efficiency, the greatest average purification efficiency is when using pure oxygen, which is 0.1 milligram per watt hour. And the last is the purity of the oxygen gas increases the removal ratio of the dye concentration. The purer the oxygen gas used, the greater the removal ratio of dye concentration from the purification process. Thank you for your attention. Wassalamualaikum warahmatullahi wabarakatuh.
Distinguished ladies and gentlemen, the participants of InCITE 2021. Today, I would like to present my paper entitled Immobilization of Xylanase on Acid Pretreatment Bentonite as Green Biocatalyst. Let me share my PowerPoint presentation first. First, I would like to let you know about what is xylan and what is xylanase. Xylan is the most common hemicellulose polysaccharide in the plant cell walls. It consists of about 30 to 35% of the total dry weight. So actually, xylan is already in the plant cell wall, and the cell wall is used for making pulp. Xylanase, as I said, as a green biocatalyst, is a hydrolytic enzyme that could hydrolyze the backbone of complex polysaccharide in xylan. So this enzyme is very effective for helping in the bleaching process in pulp and paper industry. Xylanase itself could reduce the chlorine consumption and any adsorbable organic halides in effluent by 15 to 25%. So the existence of xylanase itself is a very, very good for protect the environment by reduction of chlorine use in the bleaching process of paper making. So xylanase itself is a lignin carbohydrate complex in the pre-bleaching pulp process, so it produces small residual lignin molecule that are easier to remove by chloride. So the application of xylanase in pulp bleaching to reduce chlorine used in the application, so we call as a green biocatalyst. So this is the structure of xylan. So that's why I said that why xylanase is very useful, can help the reduction of chlorine used in the bleaching process, because actually it can cut the chain here. You see the existence of xylanase can cut all this chain, so the chlorine can easily penetrate in the pulp structure. So that's why we don't need a lot of chlorine, because there is a xylanase has already cut all these very complex chains. So I will move to immobilization technology. So why we use the immobilization technology in this enzyme, in this xylanase? Because there are some advantages. So actually it can increase the biocatalyst stability at various conditions of operation, increase the enzyme utilization. So that's why we would like to immobilize the enzyme in a matrix or carrier. So what are carriers? Many type of carriers. We can use cytosine, magnetic latex beach, or even some natural resources like bentonite or maybe duolite and also multi-wall carbon nanotube. But all these carriers are expensive, so that's why we propose the use of bentonite for the immobilization of Xylanase, because it's classified as a porous inorganic matrix. So why bentonite? Because this is a natural resources and abundant in Indonesia, not expensive, and also one of the monomorphinolite components between the two tetrahedral silicon and oxygen layers. So modification of this bentonite by acid is introduced for the natural bentonite activation procedure, because we would like to activate the surface of the bentonite, so it's easily for the Xylanase can go inside and then immobilize in the bentonite. So what are the objectives? The objectives actually is we would like to synthesize the Xylanase. So we produce the Xylanase and then we concentrate and then we purify and then we immobilize in the bentonite. So we would like to see whether we are successful for making the green biocatalyst. So this is the material and method procedure for the enzyme production and purification. Because as I mentioned before, that Xylanase are synthesized, are produced. So we produce the Xylanase in a 1.5 liter batch fermenter. So we use the media as written in the slide. And also we try to use the relativistic sperma press cake. This is the waste from the cake. They usually press the seed and then the residue is the press cake and as a waste. So we try to use this press cake to be part of the media. So that's why we can produce the Xylanase. So we also use the oxygen for the synthesis of Xylanase, and we try to maintain the oxygen rate in the 0.8 liter per minute. And we tried also to adjust the initial pH about 6, and we do the fermentation for about 5 days at 150 RPM agitation. So the sample was taken every 24 hours because we would like to analyze the activity of Xylanase. All sample actually was centrifuged for 10 minutes, and then we get the aliquot. Then the aliquot actually is the Xylanase solution. Once we get the Xylanase solution, we can measure the Xylanase activity. Then after that, we need to concentrate. We need to concentrate the crude extract actually using the Amicon ultrafiltration. Then after we concentrate, then we try to purify using the ion exchange chromatography, using the Biorex resin, and then we can get the fraction. The fraction that produced from the IEC actually is the purified Xylanase. So in the preparation of bentonite carrier, we use the 20 gram of calcium bentonite, was heated first in the oven to remove the moisture, and then we activate using the hydrochloric acid, and we try to use 1 molar, 2 molar, and 3 molar hydrochloric acid. And then we reflux, and after that we wash, and then we use it for the purpose of matrix or carrier. And after that, we try to use the FTIR, Fourier transform infrared spectroscopy, to analyze the matrix, the carrier, and also the immobilized Xylanase. So now move to the enzyme immobilization and activity. So once we activate the bentonite, and then we mix with the pure Xylanase, because we try already to purify the Xylanase, then we try to mix for 24 hours at 4 degrees, and then after that, the immobilized Xylanase then centrifuge, and then we try to wash, and then finally we get the immobilized enzyme in the bentonite matrix. And we need to calculate how much is the percentage of the immobilization, and also how much is the percentage of leaching. And so finally we know exactly what is the percentage of the final immobilization. So in the result and discussion, actually, I would like to show you, this is the Xylanase production and purification. The Xylanase activity from the production of Xylanase using the media that I have already mentioned before is about 205.9 unit per milliliter. So actually the presence of Xylanase was verified by SDS-PAGE of the enzymes. So finally we know exactly we get the Xylanase because we get the 26 and 32 kilodalton. So we can see this is the band here, and this is also the band here. You see, so this SDS-PAGE show that we actually get the Xylanase enzyme. So here M actually is the marker, the molecular marker. With present show this is actually the band that the Xylanase actually is there, but this is this actually show that there is, yes, this in the solution we can also get the Xylanase here. So actually the notation of A and C is represent before and after ultrafiltration. So we can see we can get the Xylanase here. And this is also the SDS-PAGE or Xylanase solution from second ion exchange chromatography. So we can see here, we get the Xylanase, we also get the Xylanase here. Because this is the size of the Xylanase actually as a protein is about 26 to 32 kilodalton. So this table show us about actually Xylanase solution before and after ultrafiltration. So the volume actually is first we have about almost 500 milliliter, and then after ultrafiltration, of course, it reduced because we remove all the contaminant, all the not purity substances. Then we see the protein increase after the filtration. The activity also increase. Then the total unit is also increased, and the yield of course it reduced because we try to get the purified Xylanase. Here is the FTIR analysis of modified bentonite. So when we look at the picture, then we see that this is the bentonite in the A here, in the picture of A here. This is the bentonite without the modification using the hydrochloric acid. But here we start with the bentonite, we try to modify to activate with the hydrochloric acid, and here we see here is a higher transmitter compared to the natural one. You see here is more than 80%, here is between 80 to 85. Yes, this is a increase in the transmission of the FTIR analysis. But look at this C, the figure C here. We can see here that this is also higher compared to the non-modified bentonite, and here also. We can also see all this peak here that the transmitter is higher. You see, the transmitter is higher. So what does it mean? The rise in the percentage of transmittance actually indicated that impurity in the natural bentonite, such as magnesium, calcium, aluminum, actually was substituted by the H plus ion from HCl, with hydrogen ion from HCl. Because we use the hydrochloric acid, HCl, for the activation, so we can see the higher in the percentage of transmission means that all the impurity in the bentonite, such as magnesium, calcium, is already been substituted by the H plus ion from the hydrochloric acid. And now, let's see, this is the FTIR analysis of immobilized Xylanase in the modified bentonite. So once we immobilize the Xylanase, then we try to look again in the Fourier transform infrared analysis. Then we can see here that actually this is a decrease in transmittance. You see, the value of the percentage transmittance is decreased. And here, decrease in the transmittance, we can see here. And what does it mean, the decrease in the transmittance? It means that once the enzyme is immobilized, so the percent of transmittance show that actually Xylanase has already immobilized on the activated bentonite. Because once the Xylanase is immobilized in the activated bentonite, activated carrier, so it will absorb the infrared light. Once it absorbs the infrared light, then the transmission will decrease. So this analysis show that actually the immobilization is happen. This table show us about this is the immobilization of Xylanase, then we finally get the percentage of immobilization is the best is using the 2 molar of the hydrochloric acid concentration. So we get the percentage of immobilization is about 87%. The reaching is 0.059%, and then we get the final immobilization is 87.7%. This is the best immobilization that we use 2 molar hydrochloric acid for pretreatment of the bentonite. So this result actually is good because when we compare to the previous study, usually the percent of immobilization is between 52 to 72%. But in here, we can get about 87.7%. So in this figure, we can see the percentage final immobilization of Xylanase. This is from the table, and now I put in the graph. We can see here that actually the highest is at 2 molar of the hydrochloric concentration. When we use the 2 molar hydrochloric acid concentration, they actually give the highest percentage of the final immobilization. And then now move to the conclusion. Actually, the bentonite carrier was used to immobilize Xylanase from Trichoderma ricei. Actually, the Xylanase is synthesized from Trichoderma ricei, and then the Xylanase can be produced with the 206 unit per milliliter activity, and we can see the Xylanase of purification yield is about 31.32%, and show the protein band between 26 and 32 kilodalton. There are several acid concentration used for the activation of bentonite, and we know that from the research is 2 molar of hydrochloric acid is the best. The ability to immobilize Xylanase was found in the bentonite, and then we found the percentage of immobilization is about 87.7%, which is quite good enough compared to the previous study, which are about 52 to 72%. Further study, I think, may include the application of immobilized Xylanase in pulp, which include cycle study, and also to study the kinetic parameter in pulp hydrolysis using this green biocatalyst. And I would like to acknowledge, because this work actually is has been supported by Indonesian Directorate General for Higher Education for the funding project of reference 018 SP /to LPPM 01 Ristek BRIN in 2021 this year. Thank you very much for your attention and for listening. I would like to stop my presentation here. And again, it's very nice to present this paper in front of all of you. Thank you very much.
So thank you very much. So today I would like to present our research work with the title of Rice Husk S for the stabilization of the outer interfacial layer of water in oil in water double emulsion. So here are some examples of food emulsion products. For example, butter, ice cream, milk, and mayonnaise. So what is the emulsion actually? An emulsion is basically composed of two immiscible phases, whereby one phase is dispersed in another phase. So basically we have two types of emulsion. First is oil in water type, and the second is water in oil type. But we can also have multiple emulsion. For example, water in water emulsion and oil in water in oil emulsion. But however, the single emulsion and also the double emulsion, they are thermodynamically unstable system, even though the kinetic stability could be improved. So, for example, here you can see the phenomena of the emulsion instability. A good emulsion should be like this. So, the one phase is dispersed very well in the continuous phase. But when the emulsion is not stable, the droplet may come up together, so they will form the flocculation like this. And then when the flocculation is very severe, then they will collapse, and the droplet will become bigger and bigger. So it's called coalescence. And also the droplets, the flocculated droplets, they may tend to cream, or the creaming process will occur. And then after the creaming, it will finally lead to breaking process, or the phase separation between oil and aqueous phase. And next, the emulsifier play an important role in stabilizing an emulsion. So how can an emulsifier stabilize an emulsion? You can see here is the model for the emulsifier. The emulsifier consists of two parts, which is hydrophilic, the head part, and also the hydrophobic, the tail part. So with this amphiphilic character, the emulsifier will tend to attach on the interfacial layer between oil and water, so that the tension between oil and water could be reduced, and the droplet of the inner phase will be well dispersed in the continuous phase. And here the emulsifier can be also substituted by particles. For example, if you use biosilica as a solid particle, the solid particles would adhere at the interface layer and stabilizing the emulsion. So the emulsion which is stabilized by particle is called Pickering emulsion. And next, the synthetic polymeric emulsifier may cause obesity in long term. So this is a big concern that the overweight population in Southeast Asia is increasing and increasing, and even among the kids, 1 kid in 3 kids is overweight or obese. So this may cause also by the use of synthetic polymeric emulsifiers, which is massively used in all the processed food products. And finally, the potential of rice husk silica or biosilica as a bioemulsifier would help reduce the use of synthetic polymeric emulsifiers. So what is the rice husk? You may see the composition of rice husk here. So it's composed of about 75% of organics and water, and the rest are minerals. And among the minerals or the rice husk, silica is quite dominant, of which composition is basically is around more than 90%. So rice husk is a very good source of the biosilica particle. So what is the difference between silica and biosilica? Both have the same similar formula, which is SiO2, but biosilica is generally found in the living tissues, and it has amorphous structure, in contrast to silica, which has crystalline structure. And the biosilica is generally not harmful. It is quite safe and also edible. So it can be used in the food industry. So the objective of our research is to investigate the potential use of rice husk as combined with varying pH adjustment of the outer continuous phase to enhance the stability of water in oil-in-water emulsion, supported by the kinetic study of emulsion destabilization. So we come up to the methodology. We prepare the double emulsion, but to prepare the double emulsion, we have to do two steps of emulsification process. First, we have to prepare the inner emulsion, which is water in oil emulsion. So here we have to prepare the oil phase and also the aqueous phase. And then the aqueous phase will be dispersed in the oil phase, mixed using the rotor stator homogenizer operated at 20,000 RPM for 6 minutes. And we obtained the water in oil emulsion. And then the water in oil emulsion is further dispersed in the aqueous phase, which contain 0.5% biosilica, and the pH of this aqueous phase is adjusted to be several values, for example 2, 3, and 4, while 5.7 is the pH of the mixture without any pH adjustment. And then the emulsification is conducted at 8,000 RPM for 3 minutes. And we will have the double emulsion of water in oil-in-water emulsion. To determine this emulsion stability, we just use the ratio of the height of the emulsion at certain time compared with the initial height. And then we also determine the decay rate or the destabilization rate of the emulsion and also the half time using the model of exponential decay model of 3 parameters, as you can see here. So here are the results of the water in oil emulsion, which is the inner primary emulsion. You can see here that the emulsion is quite stable from the macroscopic image, and here is the microscopic image. The droplet is quite small, which is of about several micrometers, and it's quite well dispersed in the outer aqueous phase. And here is the double emulsion prepared at several pH. This one is the sample without rice husk S. So you can see here that the oil is separated from the emulsion, but for those emulsions prepared by the addition of rice husk S, look quite stable, but you cannot see the difference really clear here from the macroscopic image. So from the kinetic study, you can see quite clearly that when pH is going down to the value of 2, then the emulsion looks stable. But then when the pH is going high, from 3, 4, and 5.7, then the stability of the emulsion is going down. So you can see here the significant difference between the emulsion prepared using rice husk S as the stabilizer compared to the control sample. The stability of emulsion increased quite tremendously, so it still retains about 80% of the emulsion stability after 7 days compared to the control sample. So here is the microscopic image of the emulsion prepared at pH 2. You can see some droplets which still contain the inner droplet, but most of them have no inner droplet. Possibly the inner droplets are diffusing out to the outer aqueous phase because of the difference in the salt gradient concentration. So here is the possible explanation of the mechanism on how the emulsion is quite stable on pH 2 compared to pH higher than 2. So when the pH is increased, the silanol, which is on the surface of the silica, will have negatively charged. So when the silica contains negatively charged, then the silica particles would repel. They would they would repel each other, and they will not agglomerate. So they will make a very sparse formation on the interfacial layer. But when the pH is reduced to 2, then the silica particle will tend to have no charge. So because at pH 2, this is called as the point of zero charge, the silica particle will have no charge. So if there is no charge, then the particle would attract each other. They would like to come together. So they will make a thick agglomeration on the interfacial layer, and they will become like barrier against the flocculation and also against the coalescence. So this will contribute to the high stability of the emulsion. And these are the results from the fitting using the exponential decay model. Here we obtain the stabilizing rate constant of about 2.8, which is 100 times much lower at pH of 2 compared to the constants obtained for the higher pH. So again, this also confirms that at pH 2, the emulsion is quite stable. This again confirmed by the calculation of the half-time. The half-time of the emulsion prepared at pH 2 is quite high compared to the half-time obtained for the emulsion prepared at other pH. So we come up to the conclusion. Biosilica in the form of rice husk ash significantly increased the stability of water in oil in water emulsion. The acidic pH of outer aqueous phase of about 2 improved the water in oil in water emulsion stability, since it could alter the aggregation and wettability of biosilica particles at the interfaces due to the chargeless particles. Thus, the lowest K of 2.48 days to the power of -1 was obtained when pH of outer aqueous phase was adjusted at 2. Higher pH resulted in higher K values with the order of 2, and half-time is about 0.28 day. Biosilica in the form of rice husk ash seems promising to be used for improving quickering emulsion of water in oil in water emulsion and suitable for low-fat food application. We acknowledge the source of the funding, and thank you very much for your attention.
Assalamualaikum warahmatullahi wabarakatuh. Good morning all. Thank you for having me. First of all, let me introduce myself. My name is Diliana Ratnasari. I'm from Chemical Engineering Department, Institut Teknologi 10 November. Today, I'd like to present about one-step electrochemical synthesis of silica-coated magnetite nanofluid. Okay, let's check. Okay, we start from the background. Magnetite is one of the most common iron oxide in nature. Magnetite has the strongest magnetic properties among other metal oxides. Magnetite is easy to agglomerate, so it needs to be functionalized with other materials, like silica. Silica has silanol group that cause the particles to be easily modified with various functional groups. Okay, electrochemical method has less energy consumption and low toxicity. Silica-coated magnetite can be used as nanofluid, which has many potential applications such as enhanced oil recovery and the emulsifier. The previous research first is Fajardo et al. In 2012, Fajardo had successfully synthesized silica-coated magnetite nanoparticles using one-step synthesis by electrooxidation of iron in a dilute sodium silicate solution. In 2019, Nurilasari et al. Has modified the configuration of electrode in the cell. The electrodes were changed from one pair electrode to multiple electrodes using an alternating monopolar configuration. Nurilasari can reduce the time till 3 hours. Okay, these two research is limited to the particle. So, our research produced nanofluid in one stage of process. Okay, now we can see the method. We use iron as electrode. The electrode dimension was 11 times 3 times 2.5 cm with the composition 82.28 Fe, 12.630, 3.28 C, and 1.81 Ca. We use multi-electrode 8 electrode in process. The electrode are arranged in monopolar alternating configuration like this. The distance between the electrode is 2 cm and the distance between adjacent electrode is 3 mm. After we configure like that, we connect it to the power supply. Okay, and then the electrolyte solution, we use sodium silicate 200 ppm plus. First research is polyethylene glycol 1%, and the second is polyethylene glycol 1% plus sodium sulfate 0.1 molar. Operating condition is 3 hours with stirring. Next, we will discuss about the result. Let's check it out. Okay, this is time evolution of the solution color during the electrolysis. And during electrolysis of silica-coated magnetite nanofluids without sodium sulfate addition. At the beginning of process, the color is colorless, then turns into white at 3 minutes and into green in 20 minutes, and yellow in 55 minutes, and the color still yellow till the end of process, 3 hours. The particles formed are FeOOH, which is shown as a yellow precipitate. Thus, this is the change of pH and color during electrolysis. This is time evolution of the solution color during electrolysis of silica-coated magnetite nanoparticles with sodium sulfate addition. At the beginning of process, the color is colorless, then turn into green at 33 minutes and turn into black at 55 minutes and turn and still black till the end of process. Okay, and then during the process, the pH changes from 9 to 11. Magnetite can be formed in 55 minutes. That means it was created at pH 11. Okay, this is a proposed reaction mechanism. Because of there are bubbles, so reaction at the cathode is reduction of water become hydrogen and OH mean, and reaction at anode is oxidation of OH mean become water and oxygen. And because the electrode is Fa, oxidation of Fa become Fa2+, and then Fa2+ plus 2OH mean become FeOH2. It indicates with the green solution. Then if AOH2 oxidize, we become FeOH2 and FeOOH and water. FeOH2 plus FeOOH become magnetite. It indicates with the black precipitate. The proposed reaction is same as with Fajaro et al. Okay, this is a XRD pattern and FTIR spectra of the particles. XRD diffraction pattern at various voltage. The pattern for all sample have only 5 peaks. 1, 2, 3, 4, 5. It corresponds to the standard magnetite pattern GCPDS 1906 to 9. Based on the identification of these particles, the particles were pure magnetite, and increasing the initial voltage did not influence the crystalline phase of the materials. And from FTIR spectra of particle show that peak of the 910 is SiO bond and there is FeO bond, so it may be occur chemical bond between SiO Fe Okay, this is a TIM image of silica-coated magnetite nanoparticles. TIM results show that the magnetite particles from have been coated with silica. It appears the silica has spherical-like structure, it indicates the difference in color. The light color of silica and the dark color is magnetite, which means there is the physical bond between silica and magnetite. It also proved with XRD and FTIR analysis. Okay, this is a sedimentation rate of sample at different voltage. The increase of voltage causes the sedimentation rate to be faster. The most stable solution in this research was at 2 volt, where the slowest sedimentation rate was 0.42 milli per minute. The XRD pattern of the samples showed they had mainly magnetite phase, and the change of voltage had no effect on the crystalline phase. FTIR showed Si and Fe compound in the particle form, so chemical bonds were formed between Fe and Se. The TEM analysis showed that the morphologies of particles were spherical-like. The increasing voltage caused the sedimentation rate to be faster. The stable fluid produced at 2 volt with a sedimentation rate of 0.42 milli per minute. This is an acknowledgement. The authors are grateful for the financial support provided by the Ministry of Education and Culture of Indonesia through the Fundamental Research Grant. We thank Mr. Ronaldo Pangidoan Sitinjak and Mr. Giga Husnil Azizi for their assistance with the experiments. Okay, that's all from me. Thank you for your attention.